Welcome back to week 12. We are covering problems in preparation for exam 3. Once again, I'm using one of the very last problems I have to choose from in Miriam and Craig, the same dynamics book that I had as a undergrad. But I look at that. I left out a T in the eighth. It's just an A. I had the second edition. Yeah, so there you go. Way back memory lane. Determine the amplitude of the vertical vibration of the car as it travels at 40 kilometers per hour over a wavy road um, whose contour may be expressed as a sine or cosine function with a double amplitude of 50 millimeters. The mass of the car is 1,800 kilograms, and the stiffness of each of the 4 car springs is this 35 kilonewtons per meter. Assume that all 4 wheels are in continuous contact of the road and neglect damping. Note that the wheelbase of the car and the spatial period of the road are the same, so that it may be assumed that the car translates but does not rotate. At the critical speed, VC is the vertical. Okay, at what critical speed? That's our goal right there, is to find. Well, actually, we have two. We have to determine the amplitude of the vibration, and then also find what the critical speed is. So this is very similar to a problem we have worked through before. So we'll make sure we can do it. We can assume that they didn't tell us anything about damping, so we're going to assume the shocks are shot. Not the spring, just the dampening, right? All it has is springs, and the shock's just no good. So let's see. We'll start off with a velocity conversion of 40 times 1,000 divided by 3,600. Of course, I could just divide by 3.6, but we're turning. The top is turning kilometers into meters. The bottom is turning hours into seconds, so that we end up with 11.11 meters per second. Other things that we were given, we know that the y, it's the base motion, is 25 millimeters, right? Of course, because they said that it was 2 times that right there, so that's good news for us. We also have the mass is equal to 1,800 kilograms, and the total K is going to be 4 times 35, or 140,000 newtons per meter. And L is 3 meters, or an L. So this is going to be really boom to boom. There's L, and that's 3 meters long, so 9 feet or thereabouts. Okay, so we can figure out the natural frequency quick enough. Oh no, we can find the forcing frequency, right? So wait a minute. Oh, we can find the forcing frequency by taking the velocity divided by the length, and then go 2 pi times it, right? So the velocity that you're traveling over the length right there is, in essence, going to give you the period, but we take the inverse of it, so it's not the period, it's the frequency. And then we need to apply 2 pi to it. So that's going to be 2 pi times 11.11, and divided by 3. And we end up with 23.27 radians per second. And then we ought to find out what the natural frequency is of the thing. And it's going to be K over M, 140,000 divided by 1,800. It's going to be equal to 8.819 radians per second. And of course, the next thing we're going to do is find out what R is going to be. 23.27, 8.819. And you find we get 2.639. this is, I'm trying to decide why I'm choosing the equation that I'm choosing. It's always a good idea to put those up there. So this is base motion. Oops. But it's not, we're not dealing with forces here. So this is really similar to some of the other problems where we had base motion. This is actually kind of more like exam 2 kind of stuff to some extent. I'm trying to think of rationale from coming back into this base motion stuff right here. Here's vibration isolation. Here's the base motion. But these are the forces being transmitted. Oh, no, I know. Okay, so we are using this equation right there, but notably, there's no damping, right? So that's what it is. That's why we're about to use the equation that we're about to use. And also, you notice that there's no damping right here. So what we're left with using that equation, I'm glad we went back over that, because this is the important thing, is to like use the right equation at the right time. We're going to go ahead and use another color. Let's see what other color we get. What other color we got? We're going to haven't used the blue yet. We're going to go x over y is 1 over, we can just call it r squared minus 1, or 1 minus r squared. It doesn't really matter to us. So anyway, so for this, so we could find out what x is going to be equal to y over that r squared minus 1, or 1 minus r squared. Doesn't really matter because it's going to be absolute value of this thing. And y is going to be, let me see, I'm trying to remember where did I put it. Oh, yeah, 25. And the r is 2.639 squared minus 1. So the x that we find for this ends up being 4.193 millimeters. Check me out. All right, check out my groove while my DJ revolves it. And okay, so what is the maximum speed? What is the car's maximum allowable, the critical speed? Well, that's going to be when r is equal to 1. So I'm kind of just trying to do this in the last little bit. Maybe I should go be just a little, okay. So when our critical speed, I'm tired. I made a lot of videos. I'm going to make a couple more. Very tired of it. The critical speed, it occurs when r is equal to 1. And therefore, you're going to get that the natural frequency is going to be equal to the forcing frequency. And we knew, so, which we know is 8.819. That is, the natural frequency is 8.819. And that we know that we had that equation, I wrote it before, was 2 pi velocity, the length right here of the thing. So we could say that that's 8.819 is equal to 2 pi v over 3. And we can find what the v is going to be is 4.211. Remember, those are meters per second. So we need to do, instead, we need to go the reverse route and take the 3,600 to turn those seconds into hours, and the 1,000 to turn those meters into kilometers. And so what we're left with is a v of 15.16 kilometers per hour. Kilometers per hour. Let's check it out to the back one here. Oh, 15.16. Yay! We got the right thing. And that's a 9-minute problem.